So this is the third video in chapter. Hi, this is the third video in chapter 16. This time we're going to look at the first of Maxwell's famous equations called Gauss's law. You'll have to excuse me if some of this isn't quite as clear because I don't have exactly mastery of all of Maxwell's equations, but I'll do my best. And I looked around the internet, and most of the time, unfortunately, Gauss's law is expressed with multivariable calculus, so pretty hard to find a video that's at our level. So we'll just do the best we can. They're not going to ask us too much about this on the AP exam anyway. So Gauss's law basically just says this. So the statement of Gauss's law that we have, you can have it in all kinds of different statements, but we can see it down here. Don't make it harder than it is. All it basically says is that the total flux through a surface, or the sum of the flux through a surface in three dimensions, is equal to the amount of charge enclosed divided by this permissivity constant, which is just a constant kind of like K that comes from Coulomb's law. So it's just a more general form of Coulomb's law. That's kind of how we want to think about it, that we can use to find electric fields. Okay, so the idea up here, they go through it a bunch. I definitely try to read this as thoroughly as you can, but basically it's just that, remember, the electric flux is this. So the electric flux is let's remember that electric flux is just like the perpendicular um, electric field lines coming out of a surface. So the derivation goes by looking at really small surfaces one at a time, and then adding all of them up for the entire surface. So you can see all those little surfaces that are added up, and you've got, this is like flux right here, right? This term right here represents that flux. So if you add up all the flux, it's equal to the charge enclosed inside the surface. Okay, so let's look at an example. So it says a charged spherical shell. So here we've got a charged spherical shell. You can see that this is supposed to be a hollow shell, but the book does talk about, and it's pretty simple. I asked you a question in the reading guide about what would happen if it wasn't hollow. What if it was solid? I think it's pretty much the same result. But anyway, you can think about that in a second. So first, what we're supposed to do is to figure out what the electric field is outside and inside the shell. So first of all, you can see in green here how they have selected a surface outside the shell. They called that radius r here. Yeah, radius r to this spot outside the actual conducting shell, which has a radius of r sub 0. Anyway, so now we're going to apply Gauss's law to that surface. So if we think about it, we've got field lines coming out because of the charge that's on that exterior surface of that shell. So I think one thing that's key here when you're reading this is it says the electric field will have the same magnitude at all points. So it's the same magnitude. That's going to be real key when we apply Gauss's law to that green surface. So now we're just going to basically write down Gauss's law. So we say, okay, the sum of E perpendicular times the area. This is like the change in area, but we'll think about it over the entire surface. So we're going to kind of think about these parts together and pretend we don't know calculus, because this is usually almost always done with calculus. That's what's hard about it at this point. So the sum of all the surface area is what this thing basically says. So the question is, why did E get to pop out? Why did that E perpendicular get to pop out? Well, first of all, let's think of why it's always perpendicular. I think that, like, since this is a sphere, the symmetry makes that it's always perpendicular. Okay, so that's one simplified part. So we don't have to worry about this little guy right here. The second part is that it said this, what I circled. The electric field will have the same magnitude at all points. I think that since this is an actual, we're going to consider it as an ideal sphere, a perfect sphere, that charge is going to distribute itself uniformly, and they even said that right here, uniformly distributed. And since it's uniformly distributed, the electric field is going to be the same at all points, all little pieces of area that we have, whether it's there or there or there, anywhere that the electric flux is flowing through. So it's always going to be the same. So in other words, we just have to think about the total. So that kind of makes sense. So we're summing it up and we're saying, well, okay, if this is a sphere, we're not just thinking of it as a circle, it's coming out at us. I guess I could try to draw that so it's actually coming out at us. To this, what's the surface area of a sphere, and that's where they got that 4 pi r squared. Okay, so don't make that too hard. So you've got E times 4 pi r squared, and Gauss's law said it's equal to the charge enclosed, which since we chose the green guy as our surface, our Gaussian surface, if you will, all of the charge that we had, or the net charge Q that they gave us, is enclosed, so we put that over the constant. So then we say solve for E, so divide by 4 pi r squared, and you get this. So this is the electric field outside any charged up sphere. Okay, and remember, even if it's not, even if they don't say it's uniformly distributed, unless there's some kind of artificial electric phenomena going on, it's going to distribute itself uniformly on that surface. Maybe unless it's like made of different kinds of metals or something like that. It's going to be uniformly distributed, whether it says that or not, pretty much. Okay. So what about if we choose our Gaussian surface inside? So now, let's erase this junk. So now we're thinking about this inner circle here. So what is the charge inside the sphere? So we kind of choose an arbitrary inside thing, and we think about, well, in that case, if we apply Gauss's law, so we say the perpendicular field over all those little tiny pieces of area has to be equal to the charge enclosed divided by the permissivity constant of free space. Remember, that's just a constant related to K. I think it's like 1 over 4 pi permissivity constant equals the K constant from Coulomb's law. Whatever, it's just some simple little thing, so don't let that worry you. But I think the thing here is if we choose this inside the sphere, how much charge is enclosed? Well, you guessed it, it's 0. So that's going to be 0 over E sub 0. So that's really just going to go away. So in other words, the E field, I mean, we're going to have stuff over here equal to 0. So I think the E field will still come out. I mean, it would still be perpendicular, but whatever. The E field is going to be 0 now, isn't it? So inside a charged up sphere, you get an E field of 0. And I mean, this should kind of make sense based on what we talked about, what you read about with the Faraday cage and inside that surface, how there's no electric field. This is kind of like a solid Faraday cage, if you will, but the Faraday cage didn't even have to be solid, right? So that kind of makes sense also, or I should say is consistent. All right, so I think we did this one. Let's look at exercise H together. So exercise H says a very long straight wire, here we go, possesses a uniform charge per unit length, so they're like saying that it's basically spread out the same amount. So okay, Q divided by L. So that's like how much it has, how much charge it has in the wire. It says show that the electric fields at points near, so points like these, yeah, near outside the wire, far from the ends. So we're pretending like the wire is kind of infinite, so it goes off maybe the negative infinity here for the purposes of our derivation at least, and positive infinity over here, just for the purposes of thinking about it. So far away, so we're kind of in the middle. So they're saying show that the E field is this. So let's think about this. Let's use Gauss's law. So you can see that they've already set up a little bit of a green surface for us. And okay, so I think we want to think about, well, let's just write down Gauss's law. So E sub t. Well, I think that was upside down. Perpendicular E field over the little pieces of area that are on our Gaussian surface. Remember, we're talking delta A right here. We're just thinking about all those little pieces of area that are on our surface, like that and so forth, okay? All right, so we've got that, and Gauss's law says that that's equal to the charge enclosed divided by the permissivity constant. So we say, okay, let's think about this. Well, remember they said to kind of ignore the ends, so they said far from the ends. So if we're far from the ends and we're thinking perpendicular, I don't think that the field lines, if you think about it, are going like this, right? They're going like out through the surface right here, right here, right here, right here, right here. Remember, when we're thinking flux, it's only the perpendicular components. So yeah, like maybe some of that some of those E lines are kind of like going out this way. You know what I mean? And like coming back down to a positive charge over there or negative charges over there possibly. But when we're doing flux, we're only thinking about things that are perpendicular. So, I mean, when we do things like that, we're going to pretend that this is, remember, we said it's like right in the middle. So we're going to kind of ignore any ones that kind of bend out through those surfaces and just kind of consider the lateral area of this cylinder. So that's kind of the approximation that's set up here. And as long as we're not near the end of the wire, it's very accurate. If we're near the end of the wire, it's not quite as accurate, but it's still fairly accurate. Because, I mean, as long as we consider that the wire is thin. Okay, so I think that when we do this, this part is going to become, I think once again we're going to have like uniform E coming out, so we can like pull the E outside of the sum. And then we've just got to think about what area we're really doing here. Is it the entire surface area of that green cylinder that we've chosen as our Gaussian surface or not? Well, I think we're really just going through the lateral area. The only amount of the flux is really only traveling through the lateral area of the cylinder. There's not really going to be any flux that's like it's like bending like this. That's not the way the flux is behaving in this situation. It's going straight outwards. As long as we're not near the end of the wire, like I said. Anyway, so that part is just going to be the lateral area. And remember, if you unfold a cylinder, so I'll draw it like this, and they've got R labeled right there. This top part is going to be 2 pi r, isn't it? Like this part right here. That's going to be 2 pi r for the circumference of our Gaussian surface. This part right here. And then we've got the length of the wire right there. So that's going to be 2 pi rl because those flux lines are going through all of this part. They're coming out kind of like out at us, if you can imagine that being straight up. I can't draw up, unfortunately, but whoa. Anyway, so that's that. They said there was an amount of charge enclosed of Q over L, and we put our constant in, and we get that the E field is Q over L, and then we've got to divide that to the other side, so we'll say times 1 over 2 pi r. Well, we just, I guess, looks like we're going to get 2 L's here and have L squared, so let's go back and think about that. Why do we not need that? I think the answer, is when I considered how much charge was enclosed. Let's just say it's the whole amount of charge. I guess I shouldn't have put this L. My mistake. So now we divide by L. That L is going to go underneath there. Okay. And then we're going to have, we'll put the epsilon naught right here, and it looks like what they have. Oh, mine was switched, but whatever. Pretty close. That's the idea. Okay. Let's look at one last thing. I don't know how good I'll be able to explain this one. I have a little trouble with it, but I think the main key is that you're just able to look at these equations, and we'll use these equations. So let's not take it too far in this class at least. So it says, show that the electric field just outside the surface of any good conductor is given by this. So is essentially Q over, so charge divided by area over an epsilon naught. So this is like, this is determining the electric field outside the surface of any arbitrarily shaped conductor. So you can see the little Gaussian surface that they've constructed here. A little imaginary Gaussian surface. Think about it there, you think about it there. Really doesn't matter where you do it, but I think the key is that you choose your Gaussian surface small enough. So it says we choose the area small enough so that E is essentially uniform over it. So it's really got to be pretty small so that you get an E field that's essentially uniform that lets you convert this part of the, the Gauss's law formulation into just E times A. And then you get this, and then you just say, hey, if I divide by A to get my E field, so if I take this part, whoa, let's go a different color here. So if you take this part and you divide by A, you get E equals the charge enclosed divided by A times 1 over epsilon naught. And then you say, hey, we can call that thing charge divided by a little bit of area. We can call that surface charge density, so the charge density on the surface. So we can call that sigma for surface. So that's just the density of charge on the surface. And we have some constant, and there we go. So I think that you don't want to think about that too much harder than that at this point, because I don't think you're going to get very far with it without calculus. So anyway, so we've got that that is true for the surface of any conductor. What I think is a little easier to understand is if you could take that for granted and you have two parallel plates. We'll be doing lots of things with parallel plates. Then it turns out that the E field between two parallel plates, where you've got positive charges flowing to negative charges between two parallel plates, and then you get the same E field between those plates as well, and it's parallel in the middle. It kind of gets not perfectly parallel at the edges, but basically it's parallel in the middle, and here is its magnitude. So we will be using that one for sure. We'll be doing lots of stuff with parallel plates and capacitors and stuff. So hope you found this useful. These are Maxwell's equations. They're meant to be dealt with multivariable calculus and surface integration and so forth. So if you're having a little bit of trouble, don't freak out about it. The idea is you choose a Gaussian surface. Let's go back to the first one. I really liked this one. Yeah, the idea here, remember, was you choose some kind of Gaussian surface where you want to approximate your E field, so like outside something that's happening, like a charged sphere. You sum up the perpendicular E fields over that surface, somehow apply a calculus or some little geometry trick like surface area of a sphere. Say it's equal to the charge inside divided by a constant, so it's really not that bad. And we'll see how it goes. Okay, that's it for this chapter. Get to work on those problems.